Good morning, everybody. My name is Hyo-soo Park. I'm professor of Department of Architectural Engineering at Yonsei University in Korea. Also, I'm director of National Center for Structural Healthcare Technology in Buildings. First of all, I'm very happy to have a chance for this presentation at this beautiful city of Elenite, Bulgaria. Today's my topic is the safety monitoring system for large-scale irregular building structures. Building and infrastructures on Earth are subject to various loadings such as seismic load, wind load, life and death. Those kind of loadings can cause structural damages on building structures in different manners. Typical failure scenario is like overturning, shear, bending, and compression failure. Seismic load is one of the major causes of building collapse. We can easily find the example of building collapse due to seismic load. This graph shows the relationship between the magnitude of seismic load and frequency of occurrence of seismic load for 60 years. As can be clearly seen from the figure, the frequency of occurrence of seismic load is increasing recently. Also, wind load can cause various problems related to safety and serviceability of building structures. This figure shows the relationship between the wind velocity and the occurrence of wind load for 60 years. For this graph, the wind velocity over 50 meters per second are used this graph. Also, we can see the frequency of occurrence of wind load is increasing recently too. Those kind of loadings like wind load, seismic load, unexpected loads can cause changes in structural performance of building and infrastructures. Is it possible to estimate the effect of loading on the structures? Or is it possible to determine current state of building structures? In recently, structural health monitoring system, which is called SHM, is used to provide real-time or near real-time information about safety of building and infrastructures. Today, I would like to share with you a new concept of structural health care system for high-rise buildings. The basic idea of a structural healthcare system is based on medical process for human care. From birth to death, the medical process consists of 4 steps. First, inspection or examination and diagnosis, and finally, treatment like surgery. Like the medical process, structural healthcare system can consist of 4 steps. First, optimal design. Optimal design for generation structural design alternatives and the selection of best design. Second stage, monitoring. Monitoring our structural responses subjected to various loadings like earthquake, wind load, etc. Third step is the assessment of safety and serviceability of building structures based on monitored responses. Finally, the repair and strengthening stage. In this context, our research group models of building or infrastructure as an organic body, like a living thing, instead of inorganic matter, like a lump of concrete or steel. Structural information can be considered as a DNA. The structural information includes all kinds of building information like structure types, materials, dimensions, etc. In that case, Each structural design is considered as a unique sequence of DNA. Then, the phenotype or the structural performance of building structure can be determined by genotype of DNA. This is the concept of structural healthcare technology. It consists of 4 modules. First module, optimization model to generation design alternatives and the selection of best design among the design alternatives. Second module is monitoring of structural responses of building structure subjected to some stimulus like various loadings. The monitoring technology includes like GPS, laser scanner, 2D scanner, motion capture system, or vibrating wire strain gauge, optic sensor, something like that. And the third module is decision making to determine the assess the safety of building structures. Final module is the repair and strengthening based on diagnosis. I strongly believe that application of this concept of structural health care system can increase the lifetime of building or infrastructures, or we can avoid the accident related to the collapse of building and infrastructures. With the application of structural health care system, a building is now an organic body with the eye for monitoring, brain for assessment, and muscle for repair. For the first step is the optimization model. In our group, we use the distributed genetic algorithm for structural optimization of large-scale structures. You know, the optimization based on genetic algorithm requires a relatively long computational time. So we developed high-performance genetic algorithm using a cluster of pieces. In our lab, we developed a cluster consisting of 16 pieces, and each PC has 4 processing cores. So we have 64 core processors in a cluster. Optimization based on genetic algorithm, the evaluation of fitness function is most time-consuming part of algorithm. So the evaluation task is evenly divided and allocated to 64 processors. And we applied the high-performance distributed genetic algorithm to seismic retrofit of 2 building examples. With the application, the wall clock time for whole iteration of structural optimization was reduced from about 30 hours to less than an hour. The efficiency of structural optimization can be found in the speed of curves. The second and third step is monitoring and assessment. Structural responses of building structures subjected to various loading can be monitored by the cutting-edge sensing technologies. It includes like a GPS, 2D scanner, 3D scanner, or motion capture system, accelerometers, or the fiber optic sensors. Based on the monitored structural responses, the safety can be evaluated by various structural analysis or structural identification method. Final step is repair strengthening of the building structures according to the assessment. Today, I have 2 examples for the application. First application is the large-scale irregular building structures. This is a DDP, which is called Dongdaemun Design Park, located in Seoul, downtown of Seoul. You can see this huge part is supported by this edge truss. The edge truss is also supported by these mega trusses. The edge truss is supported, the cantilever supported by this mega truss. So after completion of construction, the vertical deflection was measured. Also, the stress in members related to the vertical displacement are also measured. During the construction at site, it's very hard to expect that sustainable supply of electricity or communication. So we developed wireless sensor network for measurement of structural responses during construction at site. This is the wireless sensor node for the wireless sensor network in field. For this example, we use the three kinds of sensors like vibrant wire strain gauge to measure strain, and inclinometers or the laser displacement sensors. This is actual size picture of the edge truss. We deploy the sensors here and here. This is the user interface for the wireless sensor network developed for this example. This is the edge truss. During the construction of edge truss, it was temporarily supported by bent columns like this. After completion of the edge truss, the temporary support will be removed. Then displacement will occur. The displacement was measured about 60 millimeters from the wireless sense network, and the amount of 60 millimeters displacement was well matched with the structural analysis. Also, the measured displacement was verified from the direct measurement using displacement measurement system, which is called total station. It matches well with the systems. Also, we measure the structural responses of the mega columns, which is supporting the mega trusses. We deploy the full vibrant wire strain gauge at the mega columns. The strain history for about 2 years, we can get stable monitoring responses. Also, another example is that 123 high-rise building, which is located also in downtown of Seoul. This is a section of the building structure. This is typical floor plans. We use the various kind of sensors like accelerometers, inclinometers, anemometers, and the GPS, also vibrating wire strain gauge, also 5 optic sensors to measure strains. We deploy the static measurement system at belt truss and outrigger. Also, at top of the building, we deploy the GPS, anemometers, accelerometers. Also, we deploy the accelerometer for different stories. This is a concept of structural healthcare system for the 123 building structure. As a conclusion, I can say that the structural healthcare system can be a good alternative to safety monitoring of large-scale building structures. I guess it's all for today. Thank you for your attention.